Let us start by discussing gradients. So up until now, we have learned that the derivative of a function of fx is a representation of the gradient at any point of x. If I look at the parabola, the gradient on the turning point is equal to 0. It is equal to 0 because at the turning point, the tangent line would be horizontal. So in grade 9, we learned that if a gradient is equal to 0, then that line is parallel with the x-axis. So that's important to remember. The gradient at a turning point in a parabola is equal to 0. Now in this particular shape, on the left-hand side, we have an increasing gradient, and on the right of the turning point, we have a decreasing gradient. Remember that we read graphs from left to right. So from the left, I can see a tangent at any point will go upwards. You can follow what I'm illustrating. So all the gradients would be increasing towards the right. But after the turning point, the gradients would be decreasing, meaning it goes down from left to right. And an increasing gradient is a gradient that is bigger than 0, and a decreasing gradient is a gradient that is smaller than 0. You can also say an increasing gradient is a positive value, and a decreasing gradient is a negative value. Let us discuss the characteristics of the tangent line to this parabola. So what we have already discovered is that the gradient at a turning point is equal to 0. Therefore, the first derivative at the turning point will also be equal to 0. In this particular case, every tangent line on the left will have a decreasing gradient, or a gradient that is smaller than 0. And on the right of the turning point, it has an increasing gradient, or a gradient that is positive or bigger than 0. So let us move on to cubic functions. The standard formula for a cubic function is fx is equal to ax cubed plus bx squared plus cx plus d. Here I've drawn a possible cubic function. And what we need to learn is that this cubic function has two turning points. And we are no longer going to refer to turning points, but rather call them stationary points. And it has the same characteristic as a turning point of a parabola, where the gradient of the turning point is equal to 0. Therefore, the derivative at the turning point is equal to 0. But remember, we will refer to stationary points instead of turning points. So stationary points means there is no movement, there is no rate of change. So if there is no rate of change, the gradient is equal to 0. Now, if I follow the flow from left to right, we can discuss the different gradients. So from the left, up until the first stationary point, the gradient is increasing, meaning the gradient would be bigger than 0. Then, between the two stationary points, the gradient is going downwards. It is decreasing. The gradient is smaller than 0. And in moving towards the right, from this stationary point, the gradient is increasing again. So therefore, bigger than 0. it is then possible to have two tangent lines that are parallel to each other. We are still discussing a cubic function, and one possible variation of a cubic function is a function that is increasing before and after the stationary point. So in this cubic function, instead of it having two stationary points, it only has one point. And you can see from left to right that the gradient is ever increasing, except for this value right here, where the gradient would be equal to 0. That then also means that we can have a function that is decreasing before and after the stationary point. And remember, at the stationary point, the gradient is equal to 0. Now we are going to discuss the point of inflection. So in this cubic function, we have two stationary points, that is, points where the gradient is equal to 0. And the point of inflection is the point exactly in the middle of the two stationary points. And that point can be found by taking a second derivative, or simply by finding the midpoint between these two coordinates. The reason why the point of inflection is important because it's at this point where the slope or the curve of the line changes. So it's curving downwards, and now the concavity changes to the other direction. Think of the point of inflection in terms of a clock. Up until this point, the clock is moving clockwise, and at the point of inflection, the clock's direction changes to anti-clockwise. So it is a directional change in the curve. So in this cubic function, up until the point of inflection, it is concave up, and then after the point of inflection, the concavity is down. In our next example, up until the point of inflection, it's concavity down. So if I were to follow this direction, it will go down. And then after the point of inflection, it will turn to concave up. It's easy to get confused between when it's concave up and concave down. Simply what you need to do is follow the graph from left to right. If I were to draw an arrow and I ignore the point of inflection, I will see that this concavity can increase forever up. And after the point of inflection, if I follow the curve and I draw in an imaginary line, I see it will eventually continue downwards. So that is concavity down. The same in this example. From left to right, if I were to follow the slope, you can see that the graph will go down, so that's concavity down. And at the point of inflection, the direction changes to concavity up. And our last point that we need to make on the characteristics of a cubic function is the names of the stationary points. The point on the left is called the local maximum because it is higher than the point on the right, which is called the local minimum. But it can also be the other way around. For example, in this illustration, we have the local minimum on the left and the local maximum on the right. So the point that is lower is the minimum, and the point that is higher is the maximum.